In this video, we're going to continue talking about partial derivatives, but we're going to move on to higher order partial derivatives, i.e. we're going to take second derivatives, but second partial derivatives. If you recall, a partial derivative is when we take a derivative with respect to some variable, then all other variables we treat as constants. So, if we have this notation up here, f sub x, this implies that we first take the partial with respect to x, and then we take the second derivative with respect to x. So we read left to right here as far as the ordering goes. F sub y means we first take the partial derivative with respect to y, and then we take the partial of that derivative with respect to y again. F of xy, we take the first order partial with respect to x, and then whatever that is, we take the partial derivative of that with respect to y. And finally, f sub yx means we take the first order partial with respect to y, and then we do a partial derivative of that with respect to x. So if we have two variables, x and y, and we find all second order partial derivatives, there will be four of them, given here as these four. So let's go ahead and do that in our first example here. Find all second order partial derivatives of 2x squared y minus 5y cubed. So the first thing you want to do is you want to find z sub x. All right, z sub x is the partial with respect to x. So that is 4xy, and then minus 0, because there's no x in the 5y cubed part, so that's treated as a constant, so the derivative is 0. We also want the first order partial with respect to y. So 2x squared y, the derivative of that is just 2x squared. And then the derivative of 5y cubed is 15y squared. And that is it for the first order partials, but then we need to do the second order partials. We have to start with each of these though. So what is z sub x? Well, that is the that is the derivative of, the partial derivative of z sub x with respect to x. So the derivative of that with respect to x is just 4y, which we have here. Now let's do z sub xy. Well, this is the partial derivative of z sub x, but with respect to y, so that is 4x, which we have here. All right, let's do the partial of z sub y with respect to x. So this is z sub yx. And we get 4x minus 0. And then we have z sub yy. And this is negative 30y. Because again, 2x squared, that's treated as a constant here, so that derivative of that is 0. And we have that answer here. All right. Now we may have noticed that z sub yx and z sub xy are the same. That is not always true, but it often will be true. And we'll talk about when and why it might be true here in a few minutes. Okay. Now, let's find all second order partials of v, where v is equal to x raised to the y. Okay. V sub x is the first order partial with respect to x. This means that we treat y as a constant. Well, so we have our variable x and a constant y. We take the derivative by multiplying by the constant y times x raised to the y minus 1. Okay, now let's also do v sub y. Now this is a little bit different. We have x as a constant raised to our variable y. A constant raised to the variable y, if we take the derivative of that, the derivative of that exponential is the natural log of the constant times that constant raised to the exponent y. That is a derivative you may not remember, but recall if we have something like e raised to the y and we take the derivative of that, well, that is just e to the y. So we take the derivative of that with respect to y. This is just e to the y. But really, it's e to the y times the natural log of e, because we got to multiply by the natural log of the base. Well, but the natural log of e is 1, so we end up not writing that. So this is just our more general form of the derivative of an exponential. So I'll erase all of this, and we'll continue on. Again, that's just our first order partials, and this question wants us to answer find all second order partials. So let's do v sub xx. Well, here now we need to multiply by y minus 1 and derive that. This is x raised to the y minus 2, because again, x is our variable and the y is constant. And this is exactly what we have written down here. Now let's do v sub x y. So the derivative of v sub x, the partial derivative of v sub x with respect to y. Well, this right here is a product rule again, because we have y times x raised to the y minus 1. All right, so the derivative here is the derivative of the first, so 1 times the second, so this is x raised to the y minus 1, plus y, so the first times the derivative of the second. Well, the derivative of the second is again just the natural log of the base times the second. Oh, and that's exactly what we have here again. Okay, so we need to carry on and do v sub yy. Well, this is just a constant ln of x times the derivative of x raised to the y, which is another ln of x, x raised to the y. Or in other words, ln of x squared times x raised to the y, which is what we have here. And then we also need v sub y x. So this is the derivative of v sub y, but with respect to x now. And again, when I say derivative, I mean partial derivative here, i.e. we're treating x as a, oh, sorry, we're deriving with respect to x, so we're treating y as a constant. Well, this is the derivative of the first. So the derivative of the first here, the derivative of ln of x with respect to x, should be 1 over x. And then we multiply this by x raised to the y. And then we add the ln of x, so just the first, times the derivative of the second. The derivative of the second, which is x raised to the y, is just y times x raised to the y minus 1. Okay, well, x to the y over x is x to the y minus 1. And then this second term is y times ln of x times x raised to the y minus 1. So in fact, we get this again. All right. we have a couple more things to say. First, we'll talk about Clairaut's theorem, which is the equality of mixed partials. And here we suppose f is defined on a disk D that contains the point a comma b. And if the functions f of xy and f of yx are both continuous on that entire disk, then those second order partials, those mixed second order partials, are in fact equal at that given point, which you saw in general in the previous two examples that the mixed partial derivatives were equal. But there is a bit of a caveat. Again, we need some conditions to happen, and that is that the function f is defined on an open disk around that point. And if both of those functions are continuous on that open disk around the point, then the second order mixed second order partial derivatives evaluated at those points are in fact equal. Again, that was true for all points in the previous two examples, for all points in the domain. Okay. We'll move on to our very last part of these lecture notes. So the wave equation is defined by this equation up here. If we have a function u with respect to t and a horizontal position x, then the dependent variable u is called the displacement or amplitude, and the second order partial derivative with respect to t is always equal to a squared, where a is some constant, times the second order partial derivative with respect to x. Now, what does this do? Again, in this first part up here, this says that it describes the motion of a waveform, which could be an ocean wave, a sound wave, a light wave, or a wave traveling along a vibrating string. But the point is, again, that this is our wave equation, which shows up in many areas. So what we want to do here with this example is just to verify that the function u of x comma t equal to sine of x minus at satisfies this wave equation. So what do? Well, let's just find the second order partial of u with respect to t. Well, how do we do that? Well, that is the partial derivative with respect to t of the first order derivative of u with respect to t, partial derivative. So this is the partial with respect to t of, now let's take the derivative of sine of x minus at with respect to t. Okay, well, the derivative of sine is cosine. And then we need to multiply by the derivative of the inside function because we're doing the chain rule. And the derivative of x is 0 because we're deriving with respect to t. So we treat x as a constant. And then the derivative of negative at is negative a because we're taking the derivative with respect to t. Okay. So now let's take the derivative of that, the partial derivative of that with respect to t. So we have negative a, which is a constant out in front, so we just write out that constant. Now we take the derivative of cosine of x minus at. Derivative of cosine is negative sine. So this is times negative sine of x minus at, but then times a negative a again. So we have three negatives here. So this is negative of a squared times sine of x minus at. All right, so write this down and make sure you remember this. Again, the derivative with respect to t, the second order partial derivative with respect to t, is negative of a squared times sine of x minus at. Make sure you write that down. And then we're going to do the second order partial with respect to x now. All right. So this is the partial with respect to x of the first order partial with respect to x. But what is the first order partial with respect to x? Derivative of sine is cosine of x minus at. But what is the derivative of the inside here? So we got to multiply by the derivative of the inside according to our chain rule. But the derivative of x is positive 1, and the derivative of negative at, which is a constant because we're taking the derivative with respect to x, the derivative of that is just 0. So in fact, we're done with the derivative at that point. So now we need to take the partial of that with respect to x. And what is the derivative of cosine? Well, that is negative sine of x minus at. And again, we multiply by 1 because we have the derivative of x minus at is just 1. Now notice that if we multiply this by a squared, we get exactly what we got for the derivative with respect to t, the second order partial derivative with respect to t. So in fact, this does satisfy this wave equation where the second order partial with respect to t is equal to just a squared times the second order partial with respect to x. And that concludes our video on partial derivatives.